In this video, we're going to introduce the particle on a sphere problem, right? So we first introduced rotational motion by first looking at the two-dimensional particle on a ring. So now we want to add a third dimension, and so now we're talking about a particle on a sphere, but the concept is exactly the same. At the edge of the sphere where the particle is going to be located, the potential is going to be 0, and anywhere else other than the edge of the sphere is going to be an infinite potential that constrains the particle to motion along that sphere, right? So as far as what this means for us, as far as building up the quantum mechanics, is that now we have to consider a three-dimensional Hamiltonian rather than a one-dimensional Hamiltonian, right? So we got a 3D Hamiltonian that we're going to be looking at in this case. So we got h hat is going to be equal to negative h bar squared over 2m times the Laplacian, right? Where the Laplacian in this case is going to be a three-dimensional Laplacian. So we're going to have the second derivative with respect to x, and the second derivative with respect to y, and the second derivative with respect to z, right? So all three coordinates are going to play a role here. Now, the only thing, if you've been paying attention at this point, then you know that we're not going to stay in Cartesian coordinates. We are going to go to spherical polar coordinates, right? Because it's going to be way more natural to discuss these problems of rotation in terms of spherical polar coordinates. So we're going to want to convert this Laplacian to spherical polar coordinates, just like we did with the particle on the ring, right? So we're going to convert to spherical polar coordinates, right? So if we do that, then our Laplacian takes the following form, where we're going to have the second derivative with respect to r plus 2 over r times the derivative with respect to r plus 1 over r squared times 1 over sine squared theta, second derivative with respect to phi, plus 1 over sine theta, d theta, sine theta, d theta. Okay, so this is what you get when you do the conversion from Cartesian coordinates to spherical polar coordinates. Now, a few things to point out here. So what I've put in brackets here, this is common. This is a series of derivative sums that's usually referred to as the Legendrian. The Legendrian. And we usually use a capital lambda, so the Greek letter lambda, capital lambda squared, to denote the Legendrian, right? So this whole thing is what we call the Legendrian, and I'll be referring to it as lambda squared from here on out. And similar to what we saw in the particle on the ring, in the particle on the sphere, the radius is also not changing. So this derivative gone. Same thing here with this derivative. That guy's going to be gone as well. So we're just left with this 1 over r squared times the Legendrian, right? So now our Laplacian looks like this, where we just have 1 over r squared lambda squared, right? Looks more less intimidating than this one does, right? So that's what our Laplacian will simplify to. So now we can start thinking, okay, what is the time-independent Schrodinger equation going to look like, right? So what is our time-independent Schrodinger equation, right? So kind of simplifying the Hamiltonian here, we're going to end up with the following expression where we'll have 1 over r squared lambda squared psi. It's going to be equal to negative 2me over h bar squared times psi, right? So I just did the algebra there, moving this bit about the kinetic energy over, right? So this term here, right? Should have our, oh wait, yeah. So doing the algebra here, I'm just going to isolate the lambda squared here. So we got lambda squared psi. So this is going to give us negative 2mr squared e over h bar squared times psi. And so considering that now we have this mr squared term, right? Remember, this is the moment of inertia. So we can actually plug that in. So we got 2ie over h bar squared lambda squared times psi. And so kind of grouping all of this stuff together as a single value, then we're going to have the following form where I'm just going to call that stuff epsilon, right? So just grouping this stuff together, epsilon is just going to be equal to 2i e to the e over h bar squared, right? So just grouping all of that stuff together as a constant, right? I put it in this form just to make something explicit. So let me see, I got some space up here in the top corner, so I'm going to put this stuff up here. So I want to be a bit more explicit here, right? So we've got a partial differential equation here because we've got lambda squared, and psi is going to be a function of theta and phi. And so is the Legendrian as well, right? So we got a wave function that's a function of theta and phi, right? So looking at this problem, right, we have a function of two variables, right? So we started with a function of three variables. So we've actually simplified it quite a bit. But we need to find a solution to this partial differential equation. Now, just like we did when we looked at the two-dimensional particle in the box, we're going to try to see if we can come up with a general solution using separation of variables. And so that's what we're going to do in the next video. We're going to start with this form, and we're going to see if we can solve for a general wave function by using separation of variables.